So in this second part of the protein video, we are going to pick it up with different types of protein, and we're going to build upon our discussion of the hydrophobicity or hydrophilicity of the alpha amino acids. So there's two broad types of protein that can be used in structure: fibrous protein and globular proteins. And fibrous proteins tend to have external hydrophobic alpha amino acids. So essentially, if we had the fibrous protein here, so the long strands of the fibrous protein, and then jutting out we would have external functional groups, then these functional groups would be hydrophobic, so that when water came up to inspect this thing, there would be a repulsion here between the water and the fibrous protein, so the fibrous protein wouldn't be soluble. This is great if you're making tendon and cartilage and what have you. Globular proteins, on the other hand, you want them to be soluble, so they tend to have external hydrophilic alpha amino acids. So for example, if you had a big globular protein here and you had external alpha amino acid functional groups, they would all be hydrophilic, so that when water molecules came around to check this structure out, there would be favorable interactions and the water would allow the dissolving of this large structure. So that's an important thing to point out on that slide. Okay. Hierarchy of structure. So let's talk about the hierarchy of protein structure. Hierarchy of protein structure. Primary, secondary, tertiary, and quaternary. Primary essentially are the amide bonds. So the amide bonds, remember, they're also called peptide bonds. This is a very strong structure. Strong because the amide bonds are covalent. Secondary, tertiary, and quaternary are relatively weak structures, much more easily broken or easy to alter. These are just intermolecular forces because they're held together just by intermolecular forces like hydrogen bonding and dipole-dipole forces, etc. The common motif of secondary structure are, as we'll see in subsequent slides, alpha helices and beta pleated sheets. I'll give you visuals on these in subsequent slides. Tertiary essentially is an aggregate of secondary. Aggregate just means a collection, an accumulation of. And quaternary is an aggregate of tertiary structure. Okay, don't need to worry about that. This is what an alpha helix looks like. So this is one of the motifs of our secondary structure. So a motif of secondary structure. You know, it's held together via hydrogen bonding, so it's maintained by hydrogen bonding. And you can see the hydrogen bond in here. So if we look here, we've got an oxygen red. Then we've got, let's see, that, trying to figure out what that would be. I believe that's supposed to be a hydrogen. And I believe that's a nitrogen. So we've got hydrogen bonding between O and H and between H and N. Yeah. You can see it again here a bit more clearly. This dashed line in this visual here, maybe I can make the visual a bit larger. Yeah, we can see it a bit better now, can't we? This dashed line is the hydrogen bond. Again, you can see here, this is supposed to be, let's see, this schematic doesn't have the typical colors used in, not the typical colors used in stick and ball models, so it's hard to instinctively know what they are. But this looks like a nitrogen and a hydrogen. So the hydrogen that's activated by nitrogen on an amino part is now being hydrogen bonded to an oxygen on a carboxyl part. So that's an oxygen and that's a carbon. Okay, so we have hydrogen bonding keeping this together. So it's important to know what they look like and know what structure they are and know how they're held together. Excuse me. The other type of secondary structure motif are these beta pleated sheet. That's a typo. Not pleased, pleated. Pleated, if you please. Okay. So this is a motif of secondary structure. And essentially it follows this pleating like the edge of a tiramisu cake, or the way you would fold a beach towel if you were classically trained in folding beach towels, like this. And as this pleat comes around, it's held together via hydrogen bonds. And you can see them, if I make this a little bit larger, you can see them here. So let's have a look. Yeah, here they are. Here's the oxygen atom in red, hydrogen bonded to a hydrogen atom that's activated by a nitrogen atom. So this is the amine part of the structure. This is the carboxyl part of the structure on an adjacent part of the molecule. Okay. Okay, so beta pleated sheets. Ribbon diagram, how pretty is that? So sometimes we might, as chemists, want to know the glory detail of the atoms, and sometimes we want to just stand back and see the forest and not necessarily the trees, you know, to use an analogy. But we can see here, here's an alpha helix. Here's another alpha helix. This looks like a different alpha helix. And then these arrows, so clearly the alpha helix is like an alpha helix, right? Helical. The arrow, and you can see one here, you can see another one here. These are the beta pleated sheets. And then you've got this other stuff that's neither an alpha helix nor a beta pleated sheet. This is just good old primary structure. That's of no secondary structure consequence. So if you look at this, this particular protein here, which is insulin, obviously you would never look at this and say, oh, I know, that's insulin. Maybe somebody that stares at insulin structures all day might know that, but it certainly wouldn't be anyone other than those people that would know, oh, that's insulin. We can see by this type of structure that we have several disconnected secondary structures. So it looks like we have an aggregate of secondary structure. So according to our hierarchy, we have evidence of tertiary structure. So insulin exhibits tertiary structure as its highest level in the hierarchy. And a common question that I will certainly ask my students is, what's the highest level of structure in the hierarchy of this protein? Okay. So these protein structures can be held in place by different modalities. This slide names them. I think it's probably more useful to just look at them, so you can go back in the video and look at the names. I'll spend more of my time looking at the structures here. So we have well, we have good old-fashioned ionic interactions here, cation and an anion. We have hydrogen bonding here, so H bond. This we have, this would just be two aromatic rings. So you could have, this is actually something I typically don't look at in a GOB class. This is called pi stacking. I would argue a little bit exotic to look at a GOB class. But we can, at this level, just assume it's a type of London dispersion. London dispersion is definitely on the bill in a GOB class. But it's a fancy type called pi stacking, but never mind that for now. Here's more H bonding. We have these interactions here that they've colored in this pink color here. This is just London dispersion forces. So LD, London dispersion forces LDF. We have, again, ionic interactions here. And we have disulfide bridges. Disulfide bridges. These are covalent bonds, but they're very weak, and they can be broken. Okay. Let's see if there's anything down here hiding. Didn't see anything down here hiding, just another hydrogen bond at the bottom. So you can see on this model here, this is supposed to represent a beta pleated sheet. So it'll give you a sense of how these structures are held together by a variety of different intermolecular forces. Okay. Here's an example of hemoglobin, so the protein that's responsible for transporting oxygen around the body. And you can see it's a ribbon model diagram. So this is a ribbon model. Diagram. Well, I am popular today. Okay. This actually exhibits quaternary structure. And this is definitely the go-to example of that you'll typically find in a GOB class, or at least you want to not mess this one up. Why is it quaternary? Well, we can see an aggregate of tertiary. So roughly speaking, I'll try and split this into 4 pieces. Incidentally, quaternary has got nothing to do with there being 4 pieces. It's just an aggregate of things with 3 pieces. But we can see that we have a collection here, roughly. So if we look at any one of these collections, I've got alpha helices of different disparate collections. So I've got the green one, the blue one, the gold one, the red one. That alone is an aggregate of secondary. So that alone, the fact that I've got disconnected secondary structure, that's tertiary. And then I've got it again. I've got a cluster of gold, red, blue, and green here. I've got another cluster of gold, red, blue, and green here. And then finally a cluster of gold, red, blue. If I just had 2 clusters, it would be quaternary. It's got nothing to do with 4 clusters. It just coincidentally I have 4 clusters. But this is quaternary because it's an aggregate of tertiary. Okay, moving on. This is a nice visual that summarizes the hierarchy. So we have primary through quaternary, and I don't have anything more to say on that because I think we've said everything we need to about that. But definitely you can put this in context. You know, this is definitely the strong structure, and these are much weaker, and these can be easily damaged. And we'll see ways that you can damage that and consequences for when you damage that shortly. And I guess shortly is right now. So denaturation of proteins. So this is when you damage the structure of proteins. So you change the structure so it's rendered incapable of function. So e.g., when you cook food, we know that you can sanitize food. That's not the only reason we cook it. It tastes better, and it is more nutrient dense. But you can sanitize food. So if there's any microbes, if there's any bacterium, for example, in your food and you cook it, you would denature the proteins of the bacterium and render the bacterium incapable of reproducing itself and making you sick. Let's look at this slide. It's very dense, full of words, but what these methods of denaturation of proteins have in common, they're all sources of energy. Okay, they are all sources of energy. It could be light energy. We know that ultraviolet radiation is packed full of energy enough to damage our skin, can certainly change the protein structure, the hierarchy of protein structure. Chemically, we can alter it. We can add acids and bases or different chemicals here, ethyl alcohol or ethanol. This is a way to essentially fix the protein and cause irreversible chemical changes to the protein structure. So these would be energy in the form of potential energy of chemical structure. Again, we can add heavy metals, which is just adding chemical energy. The mechanisms and the details of which can be complicated and, to be honest, unnecessary at this level, but just know that they could be a chemical source of energy. And obviously acid-base chemistry again. So what these all have in common, they're all sources of energy. And how much energy do we need? We need enough energy as there is hydrogen bonds. So the energy of a hydrogen bond, or the energy of these interactions, if we provide that, we can alter the structure. Okay. There are different types of there are different types of protein, and as we said at the very early part of the previous video, one of the most important types, it's hard to say which is the most important because they're all dependent on each other, but enzymes are definitely something that we should spend a few minutes looking at. Enzymes are also known as catalysts. And what does a catalyst do? An enzyme or a catalyst lowers the activation energy of a chemical reaction. So that's what a catalyst does. As a consequence, the reaction may proceed quicker. So in this class, we don't go into the details of why it may choose to go quicker, but we do distinguish the fact that a catalyst doesn't just make a reaction go faster. That's a consequence, a potential consequence. A catalyst just lowers the activation energy. So whatever is stopping the reaction from proceeding to begin with, a catalyst can help lower that. Okay. The only reason I left this slide in is I don't really need my class to know that much about the prefix of these enzymes. They're self-explanatory anyway, but what I'm interested in is the suffix, ase, 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 ase. You guessed it, ase. So the suffix of an enzyme is ase. So for example, the enzyme that's designed to cleave the glycosidic linkage in sucrose is sucrase. So just as in our carbohydrate chapter we saw the suffix OSE for a monosaccharide or a disaccharide, a sugar, we see here ASE or ase is the suffix for an enzyme. Okay. Oh, I can no longer see the top of my slide. There we go. Okay, so what do these enzymes do? They essentially, they participate in a chemical reaction, but on average they don't get consumed or produced by the reaction. They can be regenerated to keep their numbers constant, but they tend to just facilitate a pathway from the sidelines. They have an active site, so an enzyme typically has an active site, and the substrate will dock with the active site. Okay. There's different ways, different analogies people use for this docking. A common one is the lock-in key, because the enzyme has to recognize the substrate, because what if it docks with the wrong chemical? Can it dock with the wrong chemical? How similar are these substrates? So if we use this lock-in key analogy, then a lock can sense the correct key because it's a negative of the key, right? So the mechanism inside the lock, in this case is the enzyme, it has a space that will register the correct shape of a key, and then you can operate the lock, or the docking of the key with the lock allows you to enter the room because you've registered a good interaction. So this lock-in key analogy is used often. Notice that the lock-in key is highly specific. So in general, enzyme action has high specificity. So just as the lock can tell the difference between the real key and, let's say, the wrong key, or the wrong substrate if the key now represents the substrate, an enzyme typically can recognize its substrate rather than another substrate, within reason. The enzymes can be fooled, and that's where we're going to head in a second. So there's the lock-in key way of thinking of things. There's the induced fit model way of thinking of things. So I like to think of this as the couch and derriere model. So I'm going to call this the couch and I'm going to say bottom because I don't know how to spell derriere. So let's say your favorite couch or sofa. I don't know if couch translates that well, but here's your sofa. There's the cushions. Here's the other. It's a pretty good sofa. And over time, through sitting on it, didn't realize I was going to get rid of quite so much. And it keeps going. Over time, the couch gets to recognize the shape of your bottom because you sit on it. So over time, the couch has this imprint of your behind, your derriere. So you essentially mold the couch to recognize you and nobody else. So that would be an example of this induced fit. The molecule senses the shape and it basically adapts to the shape of the substrate. Okay. We've said that enzyme activity is highly specific. I think we mentioned that already. Highly specific. It can increase the rate of a reaction, and pretty much every biological process is catalyzed. It increases the rate of reaction by lowering the activation energy, don't forget. But it can be altered. Remember, the enzyme is just a protein, and the protein's hierarchy structure can be altered via energy. So we can have a loss of enzyme function because of added energy. And that added energy can come from temperature increases or these chemical insults, for example, from acidic or basic conditions. There's just a few more slides, and essentially the next two are the most important ones. We can look at graphs showing what these enzyme functions might look like. So I'll make this a little bit larger. So the graph on the left, we have concentration versus reaction rate. Okay, so if we increase the substrate concentration, the enzyme is going to reach a maximum. So we're looking at the slope of the graph here. So there's a maximum conversion rate of our reaction, but then eventually we overload the enzyme, and at this point it doesn't matter how much more. I've essentially here I've saturated my enzyme. Okay, so we're looking at the slope, and we can see we've got maximum slope early on, and that's the maximum, well, it's not the maximum rate, so I should probably get rid of that. That will confuse if I start talking about maximum rate. So I probably should back away from doing so here. Obviously the maximum rate is here, right? That's the maximum rate. But we get saturated. Now we can start to slow down, because at this part here, we have an availability issue. Availability of free enzyme is starting to get lower and lower. Obviously, if we add more enzyme, why is that linear? Why is this a y is mx plus b relationship? It's y is mx plus b because all enzyme is free. It's free to load substrate. And the second you do, you increase the rate. So that's why it's a straight line. If we look at this graph, or these two graphs, we've got temperature and pH. This is when we can do things to poison our enzyme. So for example, when we cook, we essentially, for example, when you cook an egg, the egg has biological function when it's raw. When it's cooked, it doesn't. You've altered the structure, and you see the visible consequences of altering the structure. Or for that matter, when you cook a piece of chicken or a piece of fish, you see a physical and material alteration of that protein, and you can tell that it's lost biological function. You notice this temperature here is around 37 degrees Celsius. This is body temperature or physiological temperature. And this obviously is the environment that enzymes were designed to work in. If you cook your food, so essentially, this way you're starting to cook your food, you essentially you permanently alter secondary through quaternary protein structure. Here you don't have enough energy to alter the structure, but what you're doing, you have essentially prevented the docking of substrate with enzyme. So this is what you've done down here, and alter the protein structure is what you've done at the higher temperatures. pH, well, optimum pH, this would be the isoelectric point, and you have got acidic conditions below the isoelectric point. You've got basic conditions above the isoelectric point, and remember, this is considered high chemical energy, so you can chemically alter the structure of these proteins. This obviously is used a lot in pickling, so if you pickle food to preserve it, you can also pickle here, I believe, as well. Acidic pickling or basic pickling. But you would preserve the food by depriving it of its biological function. Okay, last couple of slides to wrap this video up. So, enzyme inhibition can be it can be intentional to deactivate an enzyme when no longer needed. Deactivate an enzyme when no longer needed. You know, an enzyme is a switch. You shouldn't turn it on unless you know how to turn it off. There's different ways that can happen. Obviously, you can be poisoned artificially, but you can naturally poison yourself to stop the enzymatic action. And there's different types of ways that you can inhibit enzyme function here. So you can have a look at this. I would recommend be aware at the GOB level. In a general chemistry class, you would look a bit more at Michaelis-Menten kinetics, and you would look at quantitatively a little bit more detail. But at this GOB level, I think just awareness that this can happen, and it can be by design. I think that's probably enough. And then any pilot needs a good co-pilot. So there are different molecules that can help the enzyme function properly, and some of these materials we'll look at later in our metabolism video, or one of the metabolism videos that we have to look forward to. So again, at the GOB level, I would just encourage my class at least to be aware of these co-pilots, where the pilot is the enzyme itself. So these co-pilots facilitate enzyme function. Okay, so that will wrap this second and I believe final video up in for proteins.